So I'm now going to move into the part of these lectures where we describe some of the string theoretic mechanisms for inflation in a little bit more detail. Just to remind you, last time we talked about the problem of modulized stabilization, where we had this picture of the extra dimensions with all sorts of stuff in them, and we discussed the kinds of terms one gets in the effective potential and so on. So one of the outcomes of this was that things like the size, L, and the string coupling strength, G string, are not good candidate inflaton fields because, for one thing, they roll toward a place of an extreme region of large internal dimensions, or towards zero coupling. And also, in any case, their potential is too steep to inflate, and the kinetic terms are boring, so it just doesn't happen in those directions. Instead, we stabilize them with a complicated arrangement of stress energy sources. So today, okay, and another thing we emphasized yesterday was that a generic expectation for compactifications would be warping. This is just a formal name for gravitational redshift inside the compactification, which again we'll make use of. So, so today I want to begin discussing the good candidates for inflation. And again, this is, for the time being, we'll stay in the context of string theory. And again, the motivation for that is partly the UV sensitivity of inflation, which we discussed at length. And also, there's another motivation which I think sort of surprised us all, which is that the methods that we use to model inflation and also particle physics in string theory has led to new ideas and a realization of possibilities that actually were easier to discover in this context than just thinking about field theory. And I say that just because it happened in that order in some cases. So even if one is just interested in the business of modeling the possibilities from the bottom up, using the kind of beautiful effective theory, for example, that Paolo's been describing, it's actually been a very useful part of the process to think about it in this framework, because that's led to the realization of certain possibilities that hadn't really been anticipated before that. So those are the basic motivations for pursuing this. And again, I want to start getting a little more specific. So I'll focus on a couple of possible scalar field inflatons that we study in string theory. And there are many variants of this, and even among these two types of fields that I'm going to list, there are lots of possibilities. But again, the idea is we have some compactification with scalar fields that need to be stabilized. Let's imagine that we've done that with the sorts of ingredients that I mentioned. And then we consider a fairly generic set of stress energy sources in this system, some of which could be things like branes, which are relatively light compared to the stress energy sources that we used to stabilize the moduli, and hence which don't carry enough energy to destabilize the size or the string coupling, but could carry enough energy to inflate. And another kind of field that comes nicely with a natural shift symmetry at a certain level, which is a good starting point for inflation, are axion fields. So we'll talk about both of these. Let me actually, since I think the brane motion is hopefully rather intuitive. I'll just draw a cartoon of a compactification, and literally you can think of a brain as a localized source of stress energy and its motion. So I'm just drawing the internal dimensions. Think of it as filling, think of it as filling 3 + 1 dimensions, and maybe some of the internal dimensions also. But transverse to it, to those dimensions, it may be able to move. And that motion is a scalar field. It's just a collective coordinate of this extended objects. And so, the brain can move. So if I do draw the 4 dimensions, the brain can move in the internal dimensions in a space-time dependent way. And so that's a scalar field. With axions, it's a little more subtle to see where those come from, but let me explain that, or give you the sort of simplest version of that next. So, axions naturally come from higher dimensional theories. Like string theory, in a way which is basically a generalization of a Wilson line. So if you think about an ordinary gauge potential field, consider, for example, a vector potential in a 5-dimensional theory that you want to reduce to 4 dimensions. So we want to reduce, say, from 4 + 1 to 3 + 1 dimensions on a circle. This is just meant to give you the essence of where axions will come from. So in string theory, we start in some higher dimensions and go down, but it's going to be basically a generalization of this. So, so we have some vector potential A mu, and let's consider a configuration where A in the 5th dimension is just given by some constant little a times the derivative of x5, the 5th coordinate, the 5th dimension. Now you might worry here that this is pure gauge. This is d of x5. But the point is x5 is on a circle. So x5 is equivalent to x5 plus 2 pi times some length L. And so A is d of something that is not well defined on the circle. It's d of something that itself is not periodic. And so this is not pure gauge. This is a non-trivial configuration of the gauge field. And it's flat. So d of A is 0. It carries no energy at this level, and it's a well-defined scalar field degree of freedom in 3 + 1 dimensions. So we get a scalar A of x and t in 4 dimensions. Are there any questions about this?
The zero mode is not gauge mode.
Correct. It's not a pure gauge mode. That's my point here. Even though it may naively look like it, it's only d of something locally. I'm sorry?
All the other very reduced dimension, all the other states are in configuration. Only the zero mode cannot be defined with the gauge level.
Well, no. I mean, there are higher modes. They're just not flat. They cost energy. I'm not actually sure what. I mean.
Zero mode is not.
Right. let's focus on this flat connection, which is not pure gauge.
So it's constant in x5, but not in the other.
Yes, 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 yeah. Yeah, exactly. I think I'm not getting your point, but.
A5 is a function also of x5.
Oh, yeah, but then that you can just redefine your coordinate. So I think, okay, now I see what you're saying. So we're interested in this thing, which is a scalar field in 4 dimensions. It's constant in x5, but nonetheless, it's not a gauge. It's not a pure gauge mode. In fact, the correct variable here is e to the I integral of a around the circle. That is a well-defined quantity called a Wilson line. I'm bringing this up because I hope it's kind of the simplest realization of an axion-like field. So, what appears in the Lagrangian, up to the funny generalized terms that I described yesterday, are derivatives of A. So this field is naturally derivatively coupled. So it naturally it starts its life with a shift symmetry. So it's not only is it a scalar field, but at the level we've talked about it so far, it has a shift symmetry. So in string theory, we have these higher dimensional form fields that we talked about last time. So we have, for example, a 2-form field, B mu nu, and for similar reasons, there's a scalar field that we obtain if we consider a configuration where this B is some scalar little b times an object which I'm just going to write as omega, which is a non-trivial. So in mathematical terms, it's a closed 2-form. It's a configuration of this field such that d of it is 0. It's flat. It carries no energy, but it's not d of anything else that is well defined. So again, back over here, we talked about this A5 sort of looking like d of something, but really it's flat, but it's not actually pure gauge. And there's a generalization of this in higher dimensions. So for all of these higher dimensional potential fields that we have in the theory, on a given internal manifold, there might be analogs of this circle that we talked about here, such that when we put these potential fields in a certain configuration, they are flat, they cost no energy, and they're not just pure gauge modes, they're physical modes. So if that's cryptic, don't worry about it. If you understand this example, just view the case in string theory as just package it in your mind as a higher dimensional analog of that, because that's pretty accurate. Are there any questions? So we'll get to this later, but the thing that will become also important is that the shift symmetry will be broken by effects like what we discussed last time briefly, where we had the combination which we called F twiddle squared appearing in the action, which was the field strength d of some A p minus 1, which is the direct generalization of electromagnetic field strengths in higher dimensions, But I just told you that there's an additional term in the complete expression for the field strength squared in string theory that involves combinations like this B times another, in this case, P minus 2 field strength. Altogether, there's a gauge invariance that's still preserved. That's something that you're exploring on the problem set. And we'll discuss this more, but this is basically where the lifting of the shift symmetry is going to come from generically in string theory. So, so the next step for us will be to discuss these two cases of scalar fields that at least potentially could be light and carry an inflationary sector within a stabilized string compactification. And so we'll go as far as we can discussing some of the mechanisms in string theory that realize this idea. Are there any questions so far about? Yeah.
Is shift symmetry, is that like a field space shift symmetry?
Yes, yeah. So in this example, the action just depends on the derivatives of A. It just depends on the field strengths, and so if you move in this scalar field direction, nothing in the action lifts that. It's a flat direction. That alone would be bad for inflation. It would not carry any potential energy, but this is at a classical level, and there are corrections to that generally. But what I'm saying is, remember the first day we considered this quadratic potential as a possibility, and we observed that part of what makes it work just from the bottom up was that the leading thing breaking the shift symmetry was this potential itself. And here I'm just saying at the level of just the electromagnetic theory, classically there's no potential at all, so this field starts out life with an exact shift symmetry. And in string theory we have analogs of this, and the goal will be to understand at what level, if at all, is that shift symmetry broken, and could it happen that the shift symmetry is broken by something that can serve as an inflaton potential? So that's the logic. So yes, long story short, it's a shift in field space. Any other questions? Okay. Okay, so what we want to do is study this inflation stuff in a way that is consistent with the moduli stabilization considerations that we talked about last time. And one of the nice things is that they are interrelated, and the moduli stabilization is kind of the ugly part. It's the messy procedure that I outlined last time that we need to stabilize those runaway moduli. And it has, it introduces limitations on the model building for inflation. But I think despite that, it's actually the case that the mechanisms for inflation in themselves are quite simple and have a certain naturalness to them that can be essentially decoupled from the complications of the stabilization procedure, although they need to be consistent. So let me just start actually by emphasizing the conditions placed by moduli stabilization before getting into the nice mechanisms, so that we address these carefully. So moduli stabilization is a limiting factor, or it's a constraint that places a few kinds of limitations on producing inflation using these lighter fields. And there are various aspects of this. One is that despite shift symmetries, et cetera, it eventually limits the range of any of these scalar fields. And various ways, depending on which kind of fields we're talking about. But one rather general point to make is that whatever the source of inflation is, if it's carried by some brane moving around or if it's carried by an axion with some additional potential terms, it is subject to the same issue that we found for the moduli potential yesterday, which is that it's going to be proportional to the factor that we needed to introduce to go to Einstein frame in 4 dimensions. Which, as we discussed last time, dilutes away to 0 as we go to large volume or weak coupling. And in particular, if we start to jack up this, inflationary potential energy to become too large, it eventually sources the moduli, and so it kicks them out of their minima. This is kind of an obvious point, but it's one worth emphasizing because, it's been missed in some discussions. There's a very simple case you can play with to see this. If you just consider stabilizing the moduli with some, let's say we focus on some direction G, and we stabilize the moduli with a 3-term structure that respects the fact that the potential goes to 0 at weak coupling, and believe it or not, this is more than a cartoon. These terms do appear pretty simply in string compactifications. So suppose we have a structure like this stabilizing the moduli, and we can all solve this system. It's a quadratic equation. You find that there is a local minimum here, which you lose if you change the coefficients A, B, and C here too much, but there's a local minimum for some range like this for these coefficients A, B, and C. And now let's consider the case where this C term carries some energy from, say, an axion times a flux. So again, we have that kind of structure that I gave above. So suppose, suppose this C, which generally depends on other directions in field space, depends on our axion. So X, let's say, is proportional to our axion field. We could call it A. Clearly, if we jack up the energy carried by this axion, we eventually lose the de Sitter minimum here, and the whole system becomes unstable. So this is something that always needs to be considered. And again, it's not a very strong constraint if one considers a field that is naturally light and whose potential energy is naturally below the moduli stabilization barriers in the problem. But anyway, this is really the only limit I know on the range of the field. Well, that's an interesting point. I think people have written models where, in some direction you end inflation in this way. People did this because they wanted to have a situation where there was low energy supersymmetry at the end of the process, but during inflation, there wasn't. And one way they accomplished that was to sort of have inflation and produce a transition from a vacuum with less supersymmetry to a vacuum with more. That's an interesting possibility. Yeah.
What is G? Example?
Well, G, I just meant G to be some combination of the runaway scalar fields, like the size or the string coupling And in general, there are many fields like this, sizes of submanifolds, et cetera, et cetera. So I'm being schematic here. I'm just collecting. If you want, you can think of this as a string coupling. It's just one combination of moduli. Okay, and any other questions at this point? Okay, so another and kind of more interesting limitation for moduli stabilization comes up in the context of small field models based on branes in warped regions. And so let me turn to that next. So compactification effects can contribute the kind of operators that we talked about yesterday that are Planck suppressed and higher dimensional but still matter for inflation. So compactification details can affect the slow roll parameters like eta or epsilon at order, well, at more than order 10 to the minus 2. And this point was made very nicely in the context of a very well-studied example of inflation in string theory. So I'll cover that next. So let's study this in warped D3 brane inflation, slow roll inflation, which we drew a cartoon of the other day, where we considered a compactification X and a highly redshifted region coming out of it somewhere. There can be others, but never mind that. Let's. So I don't know what you can see here, but this is a redshifted region. You consider a brane whose motion will become the inflaton field, and another brane, kind of its anti-partner, against which it can annihilate at the end of the process, giving a nice exit mechanism. So we already drew this cartoon, and what I want to do is just describe this class of models a bit more, and in the process explain this comment, which is related to the UV sensitivity and to the question of how what are the phenomenological features of this scenario. So there's a lot that goes into this. One of the first steps is to consider a low energy supersymmetric compactification. So this is a choice of compactification manifold which before we start introducing additional stress energy sources is Ricci flat. It's a vacuum solution. This is known as a Calabi-Yau manifold. So before adding any additional sources, we consider a manifold. I guess I called it X here. And this is known as a Calabi-Yau. And one interesting feature of this is that since we're working with low energy supersymmetry, the effective potential takes a restricted form. So it may be familiar to many of you. Let me just quickly write it down. There's a set of scalar fields which are complex. the potential depends on two functions. One, the superpotential W, which is a function only of phi and not of phi bar, and a so-called Kähler potential, from which the kinetic terms are derived, which is a general function of phi and of phi bar. And when you pick the internal manifold to have this feature, the four-dimensional theory can then be packaged in a supersymmetric way. This is not obvious if you've not seen it, but just believe me that this restriction is the same as the condition that there be a fermionic symmetry, a supersymmetry in 4 dimensions. And, well, that allows you to package everything in this way. There's an additional simplification that appears in the supersymmetric, the so-called supergravity theories that come out of string compactifications at this level, which is called Noscale structure. So what happens is that purely classically, this potential that you derive from these Calabi-Yau manifolds actually does not depend at all on the size of the manifold. Even if we introduce certain of the electromagnetic field strengths, not all of them. If you introduce all of them, you source everything. But there's a certain classical approximation where the terms here that I've written, one with a positive sign and one with a negative sign, just automatically cancel each other out. So, so classically, this potential is flat in the overall size, which I guess we've been calling L, and it's also flat in the direction. Let's now name this candidate inflaton direction phi, describing the motion of a 3-brane in this system. So I'm really sorry that I can't derive all of this for you. It would be an entire class to do so. But the statements are, well, I hope the sort of gist of it, the kind of statements that one can make are coming across. Basically, you make a special choice of a very symmetric kind of system, and when you do that, at the classical level, you find that the potential is flat in certain directions, including this direction that we're trying to use as the inflaton, this direction describing the motion of a 3-brane. Any questions at this? Yes?
So the phi is the directional one, but I don't see how it can be.
You don't see?
How it can be complex field.
Good point. So actually, it's many complex fields. So again, we made not just this choice of a flat space, but we also made the choice d equals 10, which I said yesterday is a choice that starts you with supersymmetry. And so we're talking about okay, so let me just count dimensions here. So we have a 3-brane in 9 spatial directions. So transverse to that, we have, let me just say 6 transverse directions. So actually, it's 3 complex scalars that you want to think about. I've kind of I've projected this picture onto one radial direction. Let me also rewrite at this point the metric in this warped region, which is approximately anti-de Sitter. There's actually a nicer story than that, in that it has a mild running and a confining dynamics and all sorts of interesting things, but we don't have time for that here. So it's basically an ADS throat. The direction here is R. In fact, this phi, in terms of, can you see this metric, by the way? Is this visible? Okay, so one thing what we'll use is that phi, which is the motion mode in this throat is linearly related to this coordinate r. So in terms of the string tension that we introduced yesterday, phi is actually just r, the position r of the brain divided by alpha prime. Now, there are these other coordinates. It's not really an S5, but bear with me, this is a cartoon still. So altogether we have this R and the S5, and that makes the 6 directions, which form 3 complex fields.
You package them in 3 complex fields because there's some relation between these dimensions.
Yes. Well, you're asking basically why is this supersymmetric? How do you see that it's supersymmetric? And what do you get for the effective action? I mean, at the two derivative level, despite having all these, so you can think of this warped region as being formed from a large number of other 3 branes, basically. So if you recall Juan's discussion of the ADS-CFT correspondence, it was a description of a highly warped region in 2 ways. The warped region was sourced by a bunch of branes, and on the other hand, could be described as a gauge theory living on those branes. What we've done here is basically considered a bunch of branes, and we've moved one of them away from the others. And that's basically our collective coordinate. But we've done so where there are so many of the others that they've warped the geometry, and when we try and move one away, we're still in the warped region of the geometry produced by the first large set of branes. Anyway, when you compute the effective action for this field, just in the ADS solution from this stack of branes, you find that it's symmetric under a huge amount of supersymmetry, and in particular, the kinetic term just looks like, d phi squared, where it's packaged in terms of the complex. So I'm not saying this very clearly. Transverse to a given 6 brane, there's 3 complex dimensions. So let's just actually break a little symmetry and write it in terms of 3 complex phis. It turns out that because of all the supersymmetry, this kinetic term describing motion in just flat space actually still describes the kinetic term of a 3 brane, even in the presence of the other branes. So in fact, if we get to computing the dBi action for the brane in this background, we'll see that this comes out. And so that's the statement. This discussion also allows me to emphasize something which I maybe should have before, which is this is another way of seeing why this inflaton candidate is in some sense a small perturbation on the whole structure here. There's lots of branes making up the throat, and then we're looking at one little collective coordinate as a candidate inflaton. It makes sense to think of that as kind of a leftover of moduli stabilization. It's light at subdominant compared to the bigger sources that were used to stabilize this system. So yeah, thank you for these questions. It's helping. Clear. Yeah. What do X and R? Okay, good. Let me. So I should just always write this out probably. So let's just. I'm taking a flat slicing. So this is, if you like, this will eventually be a de Sitter geometry. This is just the 4-dimensional metric. And this is the warp factor. Yesterday we wrote this as e to the a of 2a of y, and now I'm just considering a specific instance of this. Any other? Yeah.
You could probably also compactify on a non-Calabi-Yau manifold if you find something which preserves supersymmetry. Would that influence the Noscale?
This is a great question. So even if you want to preserve supersymmetry, this isn't necessary. And there's kind of an industry of work trying to write down the conditions for supersymmetry in the most general way. And it does allow some curvature, actually. And I think it is important. There's been a sort of, well, it's important for a certain interesting physics question, which is, so we talk about these high and low scale inflation models. One thing that's happened so far is that the high scale inflation models, the ones that are based on axions, fit nicely into less supersymmetric compactifications. But I think the reason for that is largely these special choices, this Noscale choice, et cetera, which is, not only a choice of supersymmetry, but it's a very special choice within supersymmetry. And so for very, simple, important, basic questions like, could there be high scale inflation with low scale supersymmetry? Your question is important. It's actually a question of current research. So it's not, the moduli stabilization has been done nicely in certain examples that are controllable, but it's far from a class, we do not have a general classification of the possibilities yet. Yeah?
Is it possible to have both things? Like, is there any advantage to having say multiple axions or both brane motion and axions would be multiple?
Well, multiple field inflation is interesting, and in the case of axions, I'll mention a possibility involving multiple axions when we discuss that case, which is a nice idea. So yeah, that's a possibility. Any other questions? Okay. Okay. Well, let's see. How are we doing? Good. Okay. So So. Okay, so given this statement, what is then done in this game is to, well, first of all, we need to treat this L. We need to stabilize that, and so one does that by some effects which go beyond this classical approximation, and I'm not going to discuss that at all, but just one does that. In particular, one can obtain a superpotential from kind of tunneling effects, quantum mechanical effects, instantons, which go like, goes like this in terms of the size, a certain axion field and another type of axion field. And once one includes this term and actually anti-partners of three branes, one can move beyond this and stabilize L. And the question is, what does that do to the potential for this candidate inflaton field phi here? And, okay, I want to summarize for you what's known about that question and how it works. Okay, so again, as I said, the next question is what happens to phi given those effects. So first of all, we can study what phi, how phi behaves just in the warped region. Well, that's not the way I want to say it. The first thing we can study is the contribution to V of phi. So we're interested in the potential energy V of the inflaton candidate phi from this moving three brane. And it has contributions from its interaction with the anti-brane here. And then it also has interactions with the rest of the compactification. And we need to consider both. So the first step that people made was to just calculate, well, this first term. And they found something quite interesting at that level. So this is basically just a question of the, this is an interaction energy between a brane and an anti-brane. They interact gravitationally, and they also interact through charges that they both carry. So these are oppositely charged under some field strength, and they are attracted by gravity, so they're net attracted to each other. And one needs to understand, the potential from the D3 bar at the position of the D3 brane, or vice versa, it's the same thing, in the warped geometry, in approximately this ADS geometry. Okay, so this is a solvable problem, and conceptually, again, it's a simple question. So the answer to this is known, and I'll write it down in terms of the coordinates r that I introduced a second ago. Where here R1 is the position of the D3, and R0 is the position of the anti-brane. And this factor out in front comes from the warping. So this is a potential energy. It has units of mass to the fourth, and the redshifting, there's a factor of G naught naught for every mass dimension. And that's this R naught to the fourth over R to the fourth. So this is the result of warping. And, well, if you take this and you translate to canonical variables, you find that this potential by itself is a very nice slow roll potential. T3, excuse me. T3 is the tension of the 3 brane. I think I'd written it as tau 3 yesterday. So, by the way, in terms of the quantities we've introduced, it's just 1 over the string coupling, 1 over G string times alpha prime to the fourth. So, okay. I'm sorry. N, sorry, okay. Thank you. N is the number of total branes that made up this throat, and N is related to R here by this relation. So just trade it for R and G string. I apologize for that. Okay, good. Any other questions? R is the ADS radius, yeah. So you can see that here in this metric. Okay, so, well, one can translate this into, as I said, into canonical variables and work out the slow roll parameters, and you find this by itself would work beautifully. And by the way, if you tried the same thing in some compactification without warping, it would fail. You would be trying to get to make the slow roll parameter small enough. You would have to make it just wouldn't work. You'd have, the Planck mass is determined by the size of the space, and to make the slow roll parameters, to make the potential flat enough, you would need to expand the space to the point where it failed. So this warping at least gives you a running start on the problem of a potentially flat, small field inflationary model. But that's not the end of the story, because as we were emphasizing all along, the slow roll parameters are sensitive to very subtle effects, such as the Planck suppressed operators I mentioned in general terms earlier. And in this context, those arise. People were careful about that, and I want to just show you a contribution that will illustrate this effect, and then also describe how it can be packaged more generally. Okay, so let's see. Yeah, so, well, one contribution is the sort of classic Ada problem contribution that you get from the Kähler potential. Okay, let me not talk about that one specifically, and let me instead give you a physical description of some effects which affect Ada at order 1 because of the interaction of this 3-brane with other stuff in the compactification. Okay, so again, recall that operators like V phi squared over m Planck squared, even though it's a Planck suppressed dimension 6 operator, it leads to a contribution to the Ada parameter, which is of order 1. And let's see microscopically how such things can arise in this sort of situation. And basically the way they can arise is that you have other sources of stress energy that I'm just kind of denoting here by these X's that are involved in the stabilization of the moduli that we know we need to do. And so we need to consider not just the potential from the anti-brane at the position of the 3-brane, but also the potential of the other stuff at the position of the 3-brane. Okay, again, conceptually simple, technically quite complicated if you wanted to add it all up. So let's just estimate this. So we have our throat, it ends at some UV position, and then we have the compactification. Let's say that this thing is of size R, and let's say that we consider some moduli stabilizing ingredient, which is also localized in all of the 6 transverse dimensions. So the potential at the UV end of this warped region, okay, by UV end, let me be clear, I mean that this redshifting effect becomes strongest as R goes to 0. That's in this direction in my picture. And then as R increases, the G0 factor gets larger and larger, and the redshifting goes away. And so that's a higher energy region. A proper, something of intrinsic mass M here has a very low energy root G0, M down here. So this is the infrared, and this is the ultraviolet region. This picture is getting ridiculously busy, but maybe another color will help. This is UV, and this is IR, and that's just a statement about the relative redshifts in the 2 regions. So here in the UV, we can figure out what the potential is of some source in these transverse dimensions of size R just by ordinary physics. So it's going to be given by the Coulomb law. So let's, again, if we just say this is has 6 transverse dimensions, the Coulomb potential, so in 4 dimensions, the Coulomb potential goes like 1 over R. If you have 6 transverse dimensions, the Coulomb potential goes like 1 over r to the 4th. It's always 1 over r to the d perp minus 2. So we have this. We have the energy source here, which is basically some moduli stabilizing energy scale. So something like this non-perturbative effect that we talked about that stabilizes the moduli will also generally source the 3-brane. And so that's the scale of energy. And then, this is times g Newton in 10 dimensions. Okay. So that's how you compute what the potential would be up here. Now the 3-brane is somewhere down in the throat. This is say the gravitational interaction. Indeed, there can be other forces, gauge forces, and so on. But there's always the gravitational interaction. So okay, so but we need to also evolve this down the throat, and here's where some of the beauty of the ADS-CFT correspondence comes in. Well, in the warped region, one can solve for, one can solve the Laplace equation basically to find how the gravitational potential varies as a function of r. So, in this region, one can solve this equation and get it expanded in general, modes that solve this equation, and that solution can basically be expanded as a sum over certain modes which behave in the throat like a power r normalized by RUV, this UV scale, to some powers delta. Now, delta here is just a way of parameterizing these mode solutions. But in the ADS-CFT correspondence, because of this relation between radius and energy scale, those deltas actually correspond to dimensions of operators in the field theory that is equivalent to this region. So one can view this in both ways, and it's useful to do that. In the field theory language, this term is proportional to our phi, our inflaton candidate, over phi UV to a power determined by these operator dimensions. Again, don't worry about that if you're not familiar with the ADS-CFT duality. You can just work. Secretly, you're working with it if you just compute on the gravity side, just compute in this geometry. But for those who are familiar enough with it, that is what these deltas mean. So in other words, to assess what happens to the slow roll parameters when we include these other effects that are present, that are necessarily present in our construction, we can do it in this very physical way. Just compute the potential at the position of our brain, which is moving around in response to all the, to its complete potential. And again, the first part of the problem in some approximately flat geometry is just the usual Coulomb law. And then we evolve further from this UV end into the warped region by the solutions of the Laplace equation in that geometry. So the upshot of this is, just from this kind of effect, is a is a contribution to the potential, which is going to scale like the brain energy, the energy that's carried by the brain times this potential field, which is if I write it in Planck units, it's something like this, times the interesting power law evolution that it has inside the worked region. So, I haven't told you enough about the moduli stabilization structure and the numbers involved to give you, a specific result for this quantity. But basically, people find when they do this in this kind of geometry that, actually, let me move this. Let me call this Planck. They find that this is indeed something of order 1, and that these compactification effects generate important contributions to the slow roll parameters. So as you can imagine, it's not just one little source here. There's tons of them. There's some complicated model with a bunch of fluxes and various sources that are important in the stabilization procedure. And so there are lots of terms like this, and the idea is that using the general structure of these solutions in the worked region, you can see what shape they can have, and how that depends on this dimension delta, which determines how important they are in the infrared region of the throat where the 3 brain lives. And by just considering all of the possibilities that you get in this way, you can convince yourself, first of all, that it is possible to tune the slow roll parameters to obtain a flat region of the potential. One example of that is a kind of inflection point-like shape for the potential. And in so doing, you really, it's sensitive to these details of the compactification. And this original 3-3 bar potential is kind of beside the point because of that. But you do see enough structure, enough independent terms that it's quite convincing that this is tunable. And most recently, people have started to study this in a kind of statistical manner, trying to putting some sort of measure on this potential and on the initial conditions involved, and sort of trying to check in what fraction of the models is do you get certain values for epsilon, for Hubble, et cetera, in this kind of background. So this model illustrates a number of important things. One is that small field inflation is a viable possibility in string theory. Another is that the sensitivity to the UV translates to a sensitivity to compactification effects that lead to a large set of terms that need to be included. And finally, let me mention one. Let me mention a couple of very basic phenomenological features of this class of examples. One is that because you're tuning these terms off each other, you aim for a small field model. In fact, one of the exercises in the homework is to reproduce a nice result of Bauman and McAllister, that's all you can do in this context. It's never going to be a large field model. And as such, the tensor to scalar ratio is way below detectable. So this whole class of models would be falsified if R is measured in these near-term experiments. There is a possibility for a positive observational signature, which has to do with cosmic strings after exit from inflation, which is probably something we won't have time to cover in detail, but the basic idea is that because of the redshifting effect, this exponential warping, it's quite easy for relics like cosmic strings to be produced at a low enough tension scale that they are viable phenomenologically, and even could be so that they're not, overwhelming the CMB. We know that they cannot account for the structure, overall, but they could be there in some subdominant level, and the warping really fits well with that in redshifting down the tension of what otherwise would be heavy fundamental strings, something much milder that is viable as a possible observational window on string theory through cosmic strings produced after exit. So for those who know what it is, this is a kind of stringy version of a Kibble mechanism that arises during the process of the brain anti-brain annihilation.
So there's no way of making things parametrically safe. There's a theorem that says you cannot make Wood-be sources sufficiently far away that this potential is small.
Is there yeah, I bet there is a theorem. I'm not sure that it's been done systematically enough to quote you as complete theorem. There is a theorem that relates the range the field can make in this geometry, for a fixed value of the Planck mass. If obviously the range that there's not this wind-up toy effect in this example. So what you see is what you get in terms of the field range, and the motion is constrained by how big the manifold is, which in turn is related to the Planck mass. So there's a nice theorem about that. It's not completely tight because you can make some sort of asymmetric compactification, but it's pretty interesting. I bet you're right that there is a theorem, but I'm not gonna claim that here. Yes.
No, I just wanted to comment that you also wouldn't win by putting all of them away in the
Wait,
you always have the contribution from the ether potential.
Say again, the.
So if Matthias is thinking that you would win by putting all of them away, so that
Yeah.
you have this contribution,
Yeah.
you don't win because you always have the one contribution and the ether cancel out.
Yeah, this is the one that I mumbled about. So yeah, so thank you for bringing that up again. There's that e to the k in the flat space approximation. K is where the kinetic terms come from. It happens to be of this form in the flat space approximation. And just expanding that, you get a order 1 correction to eta. So that alone, overwhelms this, and you have to start adding other things to tune it. So, yeah, okay. So, and again, so small field is possible. At present, I think it's a tuned scenario. So, one result of that is that within this class, you kind of prefer a small number of e-foldings, meaning the minimum that you need. But again, that's not a feature of the large field example, so that's not something to state too generally. Okay, any more questions about this case? Yeah.
You mentioned about the statistics of getting this potential rate.
Yes.
So you come more than that?
Well, I could point you to a paper. There's a you need to learn a little bit about random matrix theory to sort of get the idea. But if you put a kind of reasonable Gaussian measure on the possible terms in the potential, and you just throw darts at that space, you can get a non-trivial distribution. I don't want to cover that here actually because.
Is it optimistic or?
Well, I think the story I've told here is pretty accurate. It's eminently possible for this to happen by accident, meaning a little, fine tune of a percent, or if you include initial conditions, that brings in more. And so I don't know whether you call that optimistic or pessimistic, but it's certainly, one thing to emphasize again is that this is all being done in a very careful way that is consistent with the moduli stabilization. All of that is accounted for properly. So it's optimistic in the sense that, this is very much a viable class of examples of inflation. It's, so maybe you could say a little more about what you mean by optimistic versus pessimistic. I mean,
Well, you just said it can be done, but I guess I'm worrying that you're going to get killed by Occam's razor with that assuming everything you put in, that it's not that. So how natural is this model?
Well, okay, I'm trying to avoid expressing my own prejudices too much. So I almost don't want to comment. But let's come back to your question at the end of the whole set of lectures. My own view, and by the way, I had this view, maybe I should just full disclosure. My own view, and I had this view before I got into the question of large versus small field models, is that the large field examples are more natural. They're natural from a Wilsonian point of view. They require a smaller Hubble patch to get started, and they don't involve this kind of statistical tuning. However, happily, it doesn't matter what any of our prejudices are, because this is going to be decided by the data according to everybody's projections in the near term. So, it really doesn't matter what any of us think. The theoretical status of this is really very nicely worked out and very clean and very principled in terms of people having, again, made sure to be consistent with a very well-established mechanism for compactifying, stabilizing the moduli, computing these contributions, organizing them in terms of the ADS-CFT correspondence. It's all in place theoretically. And then, it's a matter of taste, which of the very different possibilities for inflation, you find most likely. And again, it's nice that we don't have to debate this because the data will help decide before the end of time. So I don't know. Are there any more questions? Okay. Well, so I want to get to the next kind of field, which is axion fields. And tell that story next. Because that is also a very canonical case. So I suppose we can just get started with that now and finish next time. Okay, sorry, just let me. Okay. Okay, so the first thing to do with axions is perhaps to start by, I can remind you, actually, let's start by talking about axions just as they were considered originally just in ordinary field theory. And what we'll need about them is that they have, as I mentioned before, an approximate shift symmetry. So in terms of the A I wrote before, they have a kinetic term which is often parameterized by a quantity called F. So as we discussed earlier, we had this object, this Wilson line-like variable which has a periodicity under 2 pi shifts of the field, and we form a dimensionful, scalar field, a canonically normalized scalar field with some dimension, some parameter f of dimensions of mass, and so the phi that we'll talk about is f times the axion. Sorry, say.
That should be A dot squared.
Yes, it should. Thank you. I'm bringing up this terminology just because you'll see it all over the place. The thing that's dimensionless and has a 2 pi shift is let's call that A, and then the canonical field, let's call phi, is related to that by some dimensional parameter f, and so the whole field phi has a shift by has a periodicity 2 pi f. And so these fields were originally construed to have a potential energy that is periodic with that period. So we can write it as a sine or cosine function, in general both with this periodicity f, and now I've written it in terms of the canonical field phi. So the contributions to this in field theory models tend to be exponentially suppressed because, as somebody was saying yesterday, one finds couplings of the axion to the FF dual combination of field strengths in 4-dimensional field theory. So for constant values of A, this thing is a total derivative, but it gets activated when you consider instanton corrections in the path integral. So the action has a term like this. There's this axion times FF dual. This is a total derivative. So under normal classical circumstances, it doesn't contribute anything at all, and it's at that level that the field had this exact flat potential, exact shift symmetry. But if you think about path integrating over all the configurations of gauge fields, with the Feynman weight e to the I times the action, you will get interesting contributions from this in general. So this is the story of instanton effects in gauge theories. And the result of that is the possibility of a sinusoidal potential whose coefficient can naturally be small because it's coming from instanton effects which are like tunneling effects that are exponentially suppressed. This was sort of the way that these things were thought about in pure field theory, and often still are thought about in pure field theory. So let's first explore this. I mean, what about this in itself as a candidate inflaton? So it's a simple exercise that you can do to just compute the slow roll parameters for that potential. And what you find is that eta and epsilon can be small. So we keep saying they need to be of order 10 to the minus 2. If, and only if, this f is of order or bigger than m Planck. Okay, so just work it out and you'll see this happen. Yeah, I mean, again, in general, you can include a sine as well as a cosine function there. But still, this is, from field theory point of view, just like we said for the m squared phi squared model, from the bottom up, this works. Just presume that periodicity, you're starting with a field which naturally comes with a shift symmetry, and you get a model of inflation that works. So I should say that then this works, and it makes certain predictions. It's known as natural inflation in the literature. Natural in the sense of Wilson, not necessarily in the sense of being seen in nature, but we'll find out about that again, hopefully using the upcoming CMB data. But like with that m squared phi squared model, this raises a question of whether this could actually happens in the UV in a completion of gravity. So does this happen in a UV complete, in whatever the right UV completion is? Now, of course, we don't know the right UV completion, but string theory is a good candidate. And so, we can ask this question there. And fortunately, this is one of those questions which has a nice, clean answer, despite the landscape and all the many possibilities that we have from changing the sources that we talked about in the stabilization, things like those fluxes and so on. There's a clean answer to this in any region of computational control, and the answer to that turns out to be no. So I think I have time to say this, and then if we need to do it, review it tomorrow, that's also fine. So as we mentioned earlier in string theory, we get these axions from integrating the higher form potential fields. Let's just say a P form potential field over some submanifold of the same dimension. So this is again the analog of the integral over the gauge potential over the circle that we started the day with. And so we get axions from these things. Now, their kinetic terms come from the kind of E squared plus B squared sorts of terms that that we've talked about. So the time derivative of this field A comes from this sort of F field strength squared term in the effective potential. But let's unpack this a little bit. Let me just write out the metric indices that are important here. So this term, involves these higher field strengths and hence upper metric components to contract to get the F squared there. And the main point is basically that these things scale like 1 over size L to a large power. So let me write that in a place where it's visible. So this scales like 1 over L to the 2p. And it's because of that, which is a factor in the kinetic term, that the quantity little f that we defined here is parametrically smaller than the Planck scale. So as we had before, we get a factor of, so we have a root det g, which gives us a factor of volume, and we have, or not, the string coupling does different things for different fields, but basically we have from here a factor that's going to descend to the Planck mass squared, we have this 1 over L to the 2p, and altogether what this implies is that the kinetic term is going to look like, a dot squared m Planck squared times 1 over L to the 2p. Again, there are string couplings that work out in the same way that I'm not going to write here. And so this F squared is less than m Planck. This F is less than F squared is less than m Planck squared in any situation where the size of the internal dimensions are bigger than the string size, which is where we have any control over our calculations. So in the famous landscape of string theory, we always work in regions of control of this kind. And in that entire wild proliferation of solutions, it's not true that anything goes. There's a lot of structure in this theory. And here's one example of that. This result here that axion periods just don't become super-Planckian. They are parametrically sub-Planckian in the entire understood landscape. So in this, because of this, string theory says no to that question. But because of the terms that are still on the board up there, the B wedge F squared sorts of terms, that's not the end of the story in string theory. In fact, it's just the beginning. And next time we'll discuss what really happens with axions. Yeah.
Conjecture, because this interaction strength of the pseudocos component of phi looks much weaker, and gravity F is bigger than Planck.
Well, okay, so this may be jiving nicely with that. That's not the argument I'm making here. Here I'm just making a more technical point.
But the amplitude of, or the scattering of 4 of these goes like 1 over F.
Yeah, it's true that as you start varying with respect to phi, you pull out lots of powers of 1 over F. There's the lambda. So it may. I see what you're saying. That there may be an argument to be made there. But again, this is just a much more pedestrian result. Are there any more questions?